Hey, I'm going to tell you some stuff about vectors. I don't really think that there's much here that you don't already know. So we could call it a review, I suppose. This is going to be stuff about vectors very specifically as you will need to use vectors in physics class. So what is a vector? Well, like a vector as opposed to what? Like, what is like a vector? It's a mathematical object. It's kind of like a number, except a number only has a size. And you could make a case sorry, I can't talk and write at the same time. A vector has a size, which we usually call the magnitude of it, and a direction. So it's like a number, like the size, but it's also pointing in a direction. And this magnitude is always a positive number and a direction. So you could make a case that in one dimension, and you'd be correct, in one dimension, positive and negative numbers, in other words, integers, are vectors. Because the size, the number part of it, well, that's the magnitude, and the positive or negative of it is the direction. And if you're in one dimension, there's only two possible directions, so a positive or negative sign is enough to get it done. Now, in two dimensions, positive or negative is not sufficient for direction. Because positive and negative, that's only two choices, and if you're in two dimensions, you have the full range of possible directions that something could be pointed in. And of course, if you're thinking, oh, geez, what about when we get to three-dimensional vectors? Well, that's a thing, maybe in college, whatever. We're not going to do that. And it's really, like, once you set up the two-dimensional vector stuff, what you can do with math, with vectors, three-dimensional stuff is really not much harder. But anyway, not for us. So in two dimensions, plus minus is not sufficient. So how do we represent a two-dimensional vector? We have basically two choices. And the two choices come with a few different notation options also. So one of them is to give magnitude and direction. That might seem obvious because since a vector has a magnitude and a direction, well, why don't you just say what's the magnitude and what's the direction? And the direction could be given, it's going to be an angle. It could be given in degrees or radians. Typically in physics class, a lot of the time, we're going to give it in degrees. If for some reason, like when do we need radians? Well, if you start doing calculus with trig functions, then you have to be using radians because the derivatives of the trig functions, which you already know, aren't those things if you are in degree mode. There's like weird multiples and adjustments that have to be made. So we're not doing that here. We're not going to like take the derivative of the direction function or something like that. We just need to state what the angle is. So degrees are fine. So state the magnitude and direction. For example, here is a vector. And maybe it has a magnitude of 5 and a direction 30 degrees. Now, you can state the direction. You can do all that, like north of east and at 30 degrees above the positive x-axis and stuff like that. But the default, if you just see an angle and there's no other information given, then you should assume that it's an angle measured just like we always measure angles, where we're talking about going clockwise, counterclockwise from the positive x-axis. That is the default. So if, for this, we would say this vector has magnitude 5 and direction 30 degrees. And I can just say 30 degrees, because if I don't say anything else, then the assumption is I mean going counterclockwise from positive x-axis, just the way we always do angles. And the vector might have a name. It might be called, let's say this is like the A vector. So we usually use capital letters for vectors. You can use capital or small, but they have, we know that they're vectors because they have little vector hats on them, like a little arrow, like that. And you can totally just say that that vector is equal to 5 at 30 degrees. That is totally acceptable. Now the other way to do it would be to give what are called the components of this. So here, it's just like getting from the origin to some point on the Cartesian or polar plane. You can either do like a polar coordinate thing where you say like rotate 30 degrees and then go this far, or you can say go over this much x and go up this much y. So same thing with vectors. We have those two options. So here, let's see, that's a 30-degree angle, so this would be 2.5, and since we're in physics class, this would be 2.5 times the square root of 3, but I don't think I want to write it like that, because usually in physics we want to know the decimal number, so that's about 4.3, right? A little basic baby trigonometry can get you there. And so our other option would be in, we could say in component form. We have this vector, which is vector A. Give it the same name. Sometimes I do my vector hats, I just do like the one part of the arrow, sort of a shorthand, so probably I'll do that some when I'm doing homework assignments and notes and stuff for you. It is 4.3, comma, 2.5, but instead of just writing it like a point, it gets little pointy brackets like that. That's one way of doing it. Another way that I think you did in pre-calculus, you used unit vector notation. That's an I with a little hat on it, plus 2.5j. Right, that's another way of writing that. Our book likes to use this notation quite a bit. So it doesn't mean anything different. This is just the x-coordinate and the y-coordinate if you want to think of, or the components, I should say, not coordinates. That is that. So there's some very basic geometry that applies to this situation. So given some vector, let's call it lowercase r. That's a popular name for vectors, for position vectors, kind of like a radius. So given some vector that has a magnitude of r, notice when I'm saying the magnitude, I don't include the vector hat anymore. That's just the magnitude of it, some r, at an angle of theta. And then it would have these components, which I'm going to call, for I think obvious reasons, x and y. We just need to know how to move back and forth between one and the other, and this totally is review of stuff you've known since geometry class. So if you know r and theta, then how do you find x and y? Well, if you know r and theta, then let's see. The sine of theta would be equal to opposite over hypotenuse, which means y would be equal to r sine theta. and x would be equal to r cosine theta. And it's not by accident that also on the unit circle, the x values are the cosine values and y's are the sine values. So that's how you get from this notation to this notation. And if you're given x and y, then r, how would you find r if you knew those two? Well, that's the Pythagorean theorem. And then how do you find the theta? Theta is the tangent inverse of y over x. And I'm going to say it's the tangent inverse of y, the absolute value of y over x. And then based on the signs, the SIGN, the positive or negative of the x and the y, you just figure out which quadrant. Sorry, you can't see the edge of that, can you? Maybe you can. It's always hard for me to tell when I'm filming here what exactly the edge of the screen is for you. So that just means that you do the tangent inverse of y over x in your calculator. Make sure you're in degree mode. It's going to give you an answer. If you're doing a positive number here, it'll give you an angle between 0 and 90 degrees. And then you look at the signs of the x and the y, and if it's positive, positive, that's first quadrant. Positive, negative, that's fourth quadrant. Negative, negative, third quadrant, and whatever the other one I didn't say yet must be the second quadrant. So that's that. Now, let's see, what other vector operations do you need to know? It's super easy adding and subtracting vectors is easy if you're in component form. So in other words, if you're in like the XY form, if you have the two pieces here. Because all you have to do is add up the X pieces together, add up the Y pieces together, and that, or subtract, depending on what you're doing, and that's your answer. That's it. So let me do a quick example. I'm just going to take a peek at the problems that I picked for you to do for homework, and make sure that I'm giving you everything that you need to know. Yeah, I think one example of this will be sufficient, and then that can be the end of this video. Now, in the book, they do give a couple of problems with three-dimensional vectors, which instead of having an I and a J, like an X component and a Y component, also have a K here, like the third dimension, the Z component. Nothing that I'm telling you now is different when you have a problem like that. So if you're asked to add or subtract, just do the same thing with those components. There's just an extra K piece, and it'll be good practice for us. So let's do this. Given vector A, let's say that vector is 3I minus 4j, and let's say B is 2I plus 5j. So given those two vectors, find A plus B in component form. Let's do that first. So A plus B is this plus this. I like to stack them up so you can just see what goes with what. It's kind of like putting together like terms, right? And here's the i's go with the i's and the j's go with the j's. So we add those up, and I get here 5i plus 1. You could put a 1 there. You can just put plus j, same as like with an x. 1x and x mean the same thing. Either way is fine. So that's that. And what if you want to find a plus b, but give it in magnitude direction form? Well, we have the answer here, so all we need to do is convert this into magnitude direction form. So if we were asked to do this right out of the gate, we'd just have to do this part, get the components, and then do this. Is there a shortcut to get directly to this? Well, I mean, you can if you have two vectors that are already in magnitude direction form. You could do like a law of cosines kind of thing with two vectors, but then what if you had to add 3 together? So my recommendation is if you have to add or subtract vectors and they're not already in component form, then just get them into component form by doing this. So here they were already in component form. If they weren't, I would just have done this and then followed the same process. So magnitude direction. The magnitude is going to be square root of 5 squared plus 1 squared. One of my students a few years ago started to use the name of Pythagoras, one of your favorite geometers, I'm sure, started to use his name as a verb, and we started to say that we were, with the 5 and the 1 here, that we were Pythagorizing these, and that really caught on with the whole class and with me too, so I just kind of say that now. So if I say that I'm going to Pythagorize these, that's what I mean. So that's what, the square root of 26. This is physics class, so I'm going to pop that into my calculator and tell you that that's about 5.1. And the direction is the tangent inverse of rise over run. That's y over x. So that's 1 over 5. And just going to make sure my calculator is in degree mode. It wasn't. And do the tangent inverse of 1/5, and that's 11.3 degrees. These are both positive, so I'm in the first quadrant. Right? So you could say 11.3 degrees above the positive x-axis, whatever, but we mean into quadrant 1. And when we say this into quadrant 1, we're always going into whatever quadrant from the nearest x-axis. Right? So you don't have to wonder, like, wait a minute, 11.3 degrees into quadrant 1, I could go into quadrant 1 from up here. No, always from the nearest x-axis. All right, so let's just do one more. We'll do find, how about a minus b, and let's report that answer in magnitude direction form so that I have to do the extra steps here. Okay, so a minus b, so there's a. I'm going to stack them up because I like the way that that sets up, minus parentheses, don't make that rookie mistake to forget to distribute that minus sign. There's a lot of mistakes you can make doing physics, so I don't think we can afford that one. So 3 minus 2 is 1i, and then negative 4 minus 5 minus 9j. So there's my answer in component form. So the magnitude is the square root of 82. I Pythagorize those. And that's just barely 9.1 if we go to 2 sig figs, 9.055. And the direction is I'm going to do the tangent inverse of rise over run, but I'm going to ignore the negative signs. I'm going to do the tangent inverse of 9 over 1. Tangent inverse of 9 is 83.7 degrees. And now I'm going to look at the signs and say I had a positive, negative, that is quadrant 4. And I don't know why. A lot of times when you see quadrants numbered, people use Roman numerals for that, so that's fine, or you can use regular old Arabic numerals, whatever makes you happy. That's your little vector review.